Right, then I'm going to cover section 11.5 and 11.6 in one video, I think. Now, the first thing I have to tell you is that section 11.5, there are two facts here in bullet points and in bold. I would suggest that we don't try and learn these facts as formulas. What we need to do is get an intuitive feel for how to do this sort of question, but this is definitely not a useful formula, and this, it sort of is a useful fact, but really, it's something you need to know and understand. If you understand it, we don't need to have this as a separate fact. If you don't understand it, then having it as a bullet point isn't going to help you. So at no point kind of getting these and putting them on revision cards and memorising them is going to be useful. What is going to be useful is getting a feel for how to do this sort of question. So I'll do a quick example that uses this fact. I'll talk about why this is true, and then we'll talk about section 11.6, and then we'll deal with the chapter. So example 16 is as good an example as any. So here it says, in the diagram, the points A, B have position vectors A and B respectively. It might be a good idea to look at the textbook so you can see the wording as I'm instead of just listening to me read it out. So position vector of A is little vector A. Position vector of B is little vector B. So if they hadn't already drawn it, we would know we have to imagine an origin and draw vector A and vector B out to those 2 points. The point P divides AB in the ratio 1 to 2. So here's the point P, and it divides AB in the ratio 1 to 2. Now the way I deal with that is I put these on inverted commas, because that's not 1 metre, it's not 1 centimetre, but it is half of this length here. So when I've got a ratio, I put it in inverted commas to show that this length is 1 and this length is 2, but I don't know what units I'm measuring this in. But whatever those units are, 1 unit there, 2 units there, they're in the ratio 1 to 2, okay? And it's asking us to find the position vector of P. Well, the way we do that is that the vector from A to B is vector B minus A. That's a fact that we've seen before, but if you don't remember it, you go backwards along A, forwards along B. Vector A to P is, well, how far is it along here? Well, it's a third of the journey from A to B. And a third of the journey from A to B is a third of B minus A. Okay? And then that means that O to P, that's what we're looking for. The position vector of point P is this vector here. Well, that must be vector A plus the journey from A to P. Okay, so if we'd learnt the bullet point on page 244 as though it was a formula and applied it, we'd have got this, but we wouldn't have thought about how it was working and why it was working. And I don't think really there are any questions where having it as a formula is going to help you. You're going to need to be able to apply this sort of idea in lots of different ways. So we got a third of B minus a third of A, so that is 2/3 A plus 1/3 B, and there's our answer. Okay. Now the second thing is this idea of non-parallel vectors. So if I've got a vector A, let's have vector A going this way, and we'll have vector B going this way. If I've got some vectors which are like this, some multiple of A plus some other multiple of B. Okay, so that is a bunch of A's and a bunch of B's. Okay, so if I do all those A's and then all those B's, I would end up here, right? So that vector there is some lots of A's plus some lots of B's. Well, if you think about that, it's some A's plus some B's. You can imagine this as though it is a grid drawn out of A's and B's, right? And if it is a grid made out of A's and B's, then this would be sort of our origin and this is our point. And that point only has one set of coordinates, this many B's and this many A's. Okay? So it doesn't matter which way I go, you know, I can go this way, this way, this way, up there, up there. I need to have done a total of that many B's and a total of that many A's to get me up to point P. Okay? So if I have another vector, which I know is the same as this, and it is R lots of A plus S lots of B, then the number of A's I've got has to be the same, and the number of B's I've got has to be the same. So in other words, the coefficient of A has to be the same, the coefficient of B has to be the same. okay? That's what we're doing, that's what we're thinking about. Again, thinking about that, the way it's written in that bullet point isn't the way it will sort of feel when you remember it. You maybe think about it like this, maybe you'll see examples where it will presumably become more kind of intuitive. It's not a wrong fact, it's a really useful fact, but it's not sort of helpful when stated sort of boldly and algebraically. It's perhaps a bit more helpful when we think about it like that. The last thing, section 11.6, the key here is to think about it alongside the mechanics chapter. Okay, usually these modelling sections, you're used to by now me just saying, well, these are applied questions, right? So, and particularly if you're in my class, by the time we get to this point in the textbook, I say, right, and then there's a modelling section, which means that I don't have any new information for you, but take everything from the chapter and apply it. Well, section 11.5 is take everything so far from the chapter and apply it into nasty questions. Section 11.6 should be putting that in a real-world context, and to some extent it is, right? So example 20, this orienteering race, there's nothing new there. This is just asking us about bearings and vectors and things. It's taking what we know and putting it into a sort of map sort of situation. But we must remember what we know from mechanics, and if we don't know it yet from mechanics, then we'll find it out soon, which is that displacement is a distance. Velocity is a speed, right? But they are the vector versions of those things. So vectors of velocity, displacement, and force. Velocity is like a speed, but a vector, so it's a speed in a certain direction. Displacement is like a distance, but it's a vector, so it's a distance in a certain direction. So everything you can do with velocity, displacement, time, acceleration, sorry, time is not a vector, but acceleration is a vector, forces, all of those things are vector quantities, so you can use everything from this chapter in mechanics, and particularly when you get into the chapters, well, actually, I can't say any particular chapter. It's basically everything in mechanics can be thought of in versions of vectors. So this section is reminding us of that fact, and that's quite useful to know when you are dealing with the mechanics things, and particularly when you get into the second year of mechanics, you start doing a lot of things from the first year of mechanics in two-dimensional vector situations, right? So you might have a velocity which is not along a straight line, but in 2 dimensions. Other than that, it's the usual, take what we've done so far and apply it in different situations, in different circumstances. The last chapter of the mechanics course in year 12, the first year mechanics book, is worth comparing to this as well, because there are some overlapping questions, but I've already made a film for that, part of that chapter, a video rather than a film, so you can go and check that out on the mechanics playlist if you'd like to. That's everything on chapter 11. Hope that helps.